Hello, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. Last time we talked about the nature of the bending of light due to gravity. So let's finish this off. Let's finish off the basic tests of general relativity, or at least the basic tests of the concept of the principle of equivalence. So last time I elucidated that there were four basic situations, or more specifically two pairs of situations. The first one is the idea that Einstein thought that was his brilliant idea, and one of the happiest moments of his life, this is what he said, is that you cannot tell your own weight while you're falling. Which means that there's no difference between being deep out into space, far away from any planet or any star or anything, just in the middle of space floating, and simply falling in a gravitational field. So those two things are identical. There is nothing different about them to the person doing the falling. So if we were in this room and we were out deep into space, I'd be floating, everything would be floating, there'd be no up, there'd be no down. Likewise, if we were placed in the same room and let it fall in a gravitational field, the same thing would be in effect. Okay, so the other pair of things is essentially the same thing as the previous pair, except that you have something pushing back, like the floor. So instead of freely falling, you're simply on the floor and the floor is pushing back. Well, how's that two situations? The first situation is that you're in a room very much like this, on the surface of the Earth, and here you are. The other one is as if you're in a rocket, and the rocket is accelerating upwards, and that you're on the floor of the rocket, and the rocket is accelerating upwards at exactly the same rate that something falls on the surface of the Earth, how it falls, which is about 10 meters per second or 9.8 meters per second squared. So if you were accelerating upwards in a rocket, that's indistinguishable from if you're standing on the Earth. Now, I had an interesting person on Facebook send me a note saying, oh, well, actually, the speed upward thing is not the same as being on the Earth. All right, I'll grant you that. Because his example was, let's make the spaceship 200 miles long. So if the spaceship is 200 miles long, and as it accelerates as a unit, and as it does so, everybody in that 200-mile long segment of ship experiences the same acceleration, which is 9.8 meters per second squared. However, if we had the same 200-meter ship and it was not launched yet, and it's at the surface of Earth, then the people at the bottom of the spacecraft, it's 200 miles high now, would experience 9.8 meters per second squared. But somebody in the cockpit, way at the top, 200 miles up, would have a much lower gravity, would feel the lesser effect of gravity because they're literally higher up. Now, why don't we really care about that? That's not of importance to us, because remember, the principle of equivalence is only between what we call locally inertial reference frames. So you can't really compare those two because absolutely they're different. There's no question they're different. That's how you could detect them. But I've always posited the idea that we're in a room that's relatively small, not infinite in extent, not enormous in extent, and neither did Einstein and neither do the constructs of general relativity. So general relativity does not do that. It looks for locally inertial reference frames. Or, even more specific, momentarily local inertial reference frames, meaning at this moment, it's a locally inertial reference frame. So the mathematics of general relativity does take that into account, but that's a really good point by the person who caught me on YouTube with that, which is really great. Okay, so let's look at the next step. The next step in this total analysis is the first one, because the first one, we shone a laser across the room, and we demonstrated that in a room where the laser is going across, in a gravitational field, it bends downward into the gravitational field. So if I have a laser, I'm shooting it across the room, it doesn't hit straight across the room, it hits a little lower than across the room. And that's because space-time is curved very slightly at the surface of Earth, so that light bends downward. And by very slightly, I mean if it's 10 meters, the laser is traveling. The curvature downward is on the order, if you make a circle to approximate it, it's on the order of a light year or two. So you're not going to really notice that too much at the surface of the Earth. And so therefore, the surface of the Earth, the space-time is not strongly curved. So that's an important point. But yet it is curved enough to make us feel what we call weight. All right. So let's look at the next step. Instead of shooting the laser across and seeing its trajectory bend downward, let's shoot the laser up. How does that change things? If we shoot the laser up, let's go out and look at our four situations: deep in space, falling to the Earth, in a rocket deep in space, or on the surface of the Earth. So there are 4 different setups. Let's look at the easiest one, deep in space. So again, firing a laser up or left doesn't matter whether you're deep in space. So in deep space, the laser always stays the same wavelength. It must stay the same wavelength. It's a monochromatic laser. It must stay the same wavelength. It must reach the other side. The size of everything there's no change. But remember, all freely falling reference frames are identical. And a freely falling reference frame is deep in space. That's also the same as if we're falling in a gravitational field. So take the same laboratory, again small, not 200 miles long, but like 10 or 20 meters at the most, and let it actually fall in a gravitational field. You will not be able to tell if you're in the room falling. The laser, as you shoot it up, will have the same effect as if you're in deep space. It'll look to be the same. Inside to you, there will be no change at all. So. But now that we said last time, we talked about my friend Tony. So Tony is out in deep space with me, looking at me, falling towards the Earth. He sees me shooting the laser up. He thinks it's a cry for help or something. But no, I've got airbags. I'm going to be fine. I got a parachute. I just haven't seen to deploy them yet. In any event, so what does Tony see? Tony sees the entire setup falling to Earth. And as he sees it falling to Earth, he sees a change. He notices that I'm in a gravitational field. He sees that it's different than deep space. So what's the difference? Well, I shoot the laser upwards. By the time it gets to the ceiling has descended. So therefore, the entire length of the path, according to Tony, is shorter. But I don't see a change. So if the length of the path is shorter, therefore, the entire wavelength, according to Tony, must be blue shifted. He has to see it blue shifted because that's the roof collapsing down, which actually gives a blue shift to the light at the receiver at the top of the room. So the light would see it, according to Tony. However, I don't see a change due to the principle of equivalence. Since I don't see a change, there must be a gravitational redshift that goes in exact proportion to the gravitational blue shift that is occurring as a result of me falling. Let's say that one more time. Okay, so I'm falling. As I fall, according to Tony, very distant, the roof is catching up. The roof has the detector on it. And so since it's compressing and moving towards the light, there is a Doppler shift. This Doppler shift makes it to be a shorter wavelength. Since it's a shorter wavelength, but that's what Tony should see. He says, oh, there should be a shorter wavelength. But I don't see it. I don't see it because the falling to Earth is the same as being in deep space, so which would have no change. So for me to see absolutely no change, there must be a gravitational redshift that exactly counterbalances the blue shift that occurs as I'm falling. Okay, so that leads us to the next two. So let's just posit that that exists, that there's a gravitational redshift that counteracts the known Doppler shift, because the known Doppler shift happens because Doppler shift is a fact of life that happens to both sound and light. So there should be blue, it should be blue shifted, but it's not. So therefore there must be a gravitational redshift. So let us land softly on the surface of the Earth. The gravitational redshift should still be there. So if the gravitational redshift should still be there, but now I'm not falling, I'm simply standing, experiencing gravity. Therefore, if I shoot the laser up, we get rid of the blue shift aspect, and we only have the gravitational redshift of a laser shooting upwards. So therefore, if you were to shoot a laser up a very tall building, maybe 20 meters, let's even say 20 or 30 meters, the light received at the top of the tower that you shot from the bottom of the tower, the laser going from the bottom of the tower to the top, should be redshifted, meaning longer wavelength. And that's what's observed. This has been observed experimentally, which is really fascinating. So there is a change due to the gravitational field. And just for rounding out purposes, let's look at the fourth situation way out into deep space. So if I'm in deep space, and I'm accelerating upwards because I'm in a rocket that's accelerating upwards, I don't see any difference except like it feels like a gravitational redshift to me. So for me, I see it being a redshift. That's fine. It's the same as being on Earth. But what does my friend Tony see, who's far away and outside? How does he perceive it? Well, he perceives it in the following way. After I shoot the laser tries to catch up with the roof that's receding away. And again, that's a Doppler shift. And so there's a Doppler shift according to Tony because the roof is receding away from the laser. So Tony says that I should see it being redshifted, and I do. So there you go. So it's a very interesting thing that shows the equivalence of falling in a gravitational field to actually to freely falling. Every freely falling reference frame is identical. That's the current idea about general relativity that's really fascinating. And funny enough, it's actually borne out by experiment, which is really kind of strange. But let's actually take apart this thing about shooting a laser straight up and down. We saw before in a previous lecture how we looked at like a special relativistic clock where the laser bounced up and down inside a tube, and we just had to move the tube moved to the left, and that actually gave us the speed of things and showed that we have a time dilation. Time dilation. But wait a second. Let's go back and look at our gravitational redshift a little bit more carefully. So I take my laser, I shoot it to the ceiling, it experiences a redshift. But remember, the wavelength and frequency of light, the product of the wavelength of light times its frequency equals the speed of light, which is a constant. It never changes. Remember, the speed of light is a constant no matter who's doing the observing. So, if I'm going to look at that way, if the wavelength of light has changed to be bigger, then the frequency must change to be smaller. So that means that a smaller frequency means a larger time interval. So what we're actually showing, because the frequency is an inverse of a time interval. Like, to be specific, the speed of light is 3 times 10 to the 8th meters per second, and what are the units of wavelength? The units of wavelength are meters. What are the units of frequency? Hertz. A hertz is a cycle per second, or a wave per second, or a unit per second, or something happening every second. So it's 1 over seconds. So that's an inverse of a time, and an inverse of a time is just inverse of an inverse of a time is a time. So when we look at the reciprocal of a frequency, we get a time interval. So if you make the wavelength longer, you must make the frequency shorter. If the frequency is shorter, its reciprocal, a time interval, is longer. So therefore, a clock runs slower, deeper in a gravitational field. And this also has been borne out by experiment, which is really something. In fact, the clock differences between the satellites that manage your GPS system, so everybody uses GPS if you're in the Western world or Europe or, well, practically everywhere. It's actually pretty universal now. If the satellites and the GPS receivers that you use in an iPhone or a Droid or a dedicated machine that actually does it, if those things did not take into account the time dilation effect due to the difference in altitude of the satellites way out in space, way out in orbit, high in orbit above the Earth, and the difference in this rate of progression of the clocks on the ground, if that was not taken into account, your GPS would be off it by a long distance in only a few hours. So general relativity's corrections to space and time are experimentally borne out. And that's a really weird thought. So in sum, we've got 2 major things that really help us to try to help convince us that space-time is curved. And one of them is the path of light being changed by going across a gravitational field, or even up or down a gravitational field. The path is changed. The length, the direction of light, or the direction of any falling object, or direction of any object moving through a gravitational field, is deflected by the gravitational field. So that is specifically light, because that makes it most dramatic. But when we look at light specifically, it bends, it changes direction. So that feels like we should be thinking about curvature of space-time, because it follows the lay of space-time, because light always goes the straightest possible path. And since light goes straightest possible path, if that path is curved, then therefore space-time is curved. And then what about the time part of space-time? Well, we see that if we're deep in space, there's no change. But if we're in a gravitational field, we change lengths. Lengths change, meaning wavelengths. And therefore, time is changed, and as time is dilated, time changes. So we can think of time as curving towards a black hole, if you wish. Actually, that's not, or towards into a gravitational field. Meaning, the farther down in the gravitational field you go, the greater the time dilation exists. So if you wish to live forever or wish to live a long time, then fly at high altitude. Become a pilot or a airline, or somebody who works the halls who works on a plane all the time. You might gain a quarter of a millisecond if you did it for 30 years. So it's not a lot, but it's actually measurable, which is fascinating. So these things help us to elucidate the idea that space-time is curved. But I'd like to finish with an alternate way of thinking about the nature of curved space-time. Frequently, and this is going to get kind of wonky and silly and mathy, so please bear with me. There's a researcher, Andrew Hamilton, over at Colorado, who has some really interesting thoughts about how you can reformulate the equations that show you how to measure the distance in space-time you go. So remember we kind of tried to break up the two things, but really you got to put them together as two separate things, because you don't always just point a laser up. You're pointing up into the side a little bit, and you're not necessarily falling straight into a gravitational field. You're falling maybe at an angle. So space and time, therefore, are linked. And so if you want to know the total distance in space-time, not space or time, but a combination of the two, meaning space-time, which is an invariant if you change coordinates, which is what we mean by a metric. So this particular quantity of length in space-time, if you want to measure it, you can actually reformulate what we call the Schwarzschild metric. And the Schwarzschild metric is a way of determining the lengths of space-time near a spherical, non-rotating star. So a really close approximation to most stars is the Schwarzschild metric. It's very close. It's also the weakest limit of the Schwarzschild metric, meaning very low masses and very slow speeds, gives you what we would call Newtonian gravity. So taking the Schwarzschild metric and reducing it down to Earth level type of things, it's a complicated equation, but the complicated equation can be reduced to what we call Newtonian gravitation, which is neat. So really, we can actually derive Newton's laws by looking at lengths in space and time, which is a really interesting thing, and I'll leave that to intrepid explorers of the internet. If you wish to go look up the Schwarzschild metric, in fact, I'll probably put a link for it below on the YouTube channel and so forth. But what we want to look at then is a different way of approaching it. So the Schwarzschild metric assumes that time changes and that lengths change as you get closer to a mass. But let's posit for a second a slightly different way of thinking about it. Imagine the following, that you're a fish and you're a salmon, specifically a salmon, swimming upstream. And if you wish to swim upstream, you have to swim against the current. And the current goes fast enough that it tries to wash you back down. But if you're a very strong salmon and you don't get eaten by a bear, you make it all the way back up to the spawning pool and make babies, and then that's the end of you as a salmon. But we can think of fish swimming upstream. So there's a current going against the fish swimming, and the fish is going against the current. Now, if the current is too strong, the fish gets washed down the stream. This is the analogy we're going to work on. So imagine now that light is the fish. So light is the fish. If light is the fish, then space-time itself can be considered to be flowing. You can reformulate the Schwarzschild metric in order to make it look like that space is flowing, as though it's a rain model, as though space is raining towards mass. And as it rains towards mass, it drags anything with it and pushes it down as it falls. So it's not that you're falling in the lay of the land, it's that space itself is flowing like a river towards mass. And so light it can only go at one speed, and it gets slowed down. This is different. It gets slowed down as it tries to swim against the flow of space. So space itself is flowing towards mass. And as it flows towards mass, light can only go so fast, and what we call the Schwarzschild radius, or the radius of a black hole, that flow of space-time equals the speed of light, and therefore the fish just stays. So we can look at it in a slightly different way. So let's look at our two previous examples, starting with the time one. So if we point our laser up, light is going up. We can think of the light as photons, as packets of light swimming against the flow of space-time as they're raining down on top of it. And the photon fish, lose energy as they rise. So they have to expend energy as they rise against the current of space. So why do you feel weight? You feel weight on the floor because space-time is rushing through you, pushing you down towards the mass. That's a really interesting visual. And in fact, the mathematics work out to be exactly that. You simply transform the coordinates of the Schwarzschild metric into this rain metric, and they're equivalent. So you can actually speak of space-time as raining towards mass or flowing towards mass, or that space and time flow towards mass. So what about the bending of light that goes across? Well, take a waterfall and try to throw something through the waterfall, across the waterfall. It's going to get picked up and get pushed down the waterfall. It's the same thing. So a waterfall model of space-time as it flows towards mass is extraordinarily elusive. It is very evocative and, in fact, mathematically equivalent to what we call the Schwarzschild metric. And the Schwarzschild metric itself is exactly the thing that was derived back in the early part of the 20th century by Carl Schwarzschild, and after he solved the equations of Einstein's relativity in order for a spherical non-rotating mass. And then that metric was re-derived in this rain metric many times. But typically you won't find this rain metric anywhere, but it's much easier to understand. We think of space-time as flowing towards mass, and in fact mathematically it's equivalent to the Schwarzschild metric, so it actually works. So and it's much more helpful to think of it that way. Rather than space-time being thought of as curved, it still is curved, but we can think of space-time as simply flowing towards mass. But where does it go? See, you can replace then there's the age-old question. I hear it out there, the old question of, well, if space is curved, what's it curving into? Can now be replaced by the even funnier question, well, if space is flowing towards mass, what's it flowing into? Like, where is it going? That's a good question. It's a good question. Can't really answer that one. Not going to try. Not going to try either one of those. But we can probably answer them by getting close to the idea of what we call bulk space. And I'll invite you to go look at Kip Thorne's websites and his videos on the nature of what bulk space is. We can think of an additional space dimension, and that space dimension is the place into which it's flowing or curving. That's another way of talking about it. So I invite you to go look that up, but that will take you down a deep, deep internet rabbit hole. So make sure you look up Kip Thorne and the bulk dimension. He used it in the movie Interstellar, so be prepared for that. All right, so that's kind of does it for a lot of our discussions on gravity. We'll come back to gravity when we finally someday talk about black holes. And then we might even talk about gravity in other contexts as well, with the moon and the tides, because that's kind of important to say, well, how do the tides happen? Well, they happen because of gravity, so what's that all about? In any event, we'll see you next time.